Hi. Hi, welcome to the panel session, Machine Learning for Power System Modeling and Control. My name is Ling Fan. I'm from University of South Florida. The title is Inverter-Based Resources IBR Model Identification, Black Box Approach versus Gray Box Approach. The current power grid has a need to do IBR modeling, and those IBRs are black boxes from the perspective of grid planners and operators. The reason is that technology confidentiality. So we want to know how to model IBRs from measurement data, and this is essentially system identification for real-world engineering, and we'll cover a black box approach and a gray box approach. Further, we also want to discuss how to better prepare our students for the new challenges in the industry. First of all, let me go through the dynamic modeling of the white box approach. Suppose we want to have high fidelity models, including everything is known, and the end result is an LTI models. What is the important steps? The first step is averaging techniques developed in 1970s by power electronic people to make sure those discrete switching sequences can be get rid of, so that we only have fundamental component of 60 Hz and waveforms are smooth. That we have these EMT models called electromagnetic transient model in static frame. A lot of PESGM models and MATLAB SimSCALE models are this nature, and state variables are sinusoidal at a steady state. And these models run pretty slow, and we want to do one more step to do Parkes transformation developed in the 1920s to convert EMT models to DQ frame. Then the state variables are constant at a steady state. From there, we do small disturbance perturbation or numerical perturbation to grab the linear models. Once we have the linear model, we basically have everything. For example, the eigenvalue analysis, participation factor analysis. We can analyze a lot of mechanisms for the various of dynamic, for example, inter-area oscillations. And a lot of tools can lead to LTI models, for example, PSLF and PSSE that are used a lot in the grid industry. One particular example is this East Interconnection quarter-Hertz inter-area oscillation mode. Using this participation factor analysis or multi-shape analysis, we can see these are the two groups generator red and blue oscillating against each other. And modeling practice for the conventional grid, you can find a lot in the power system stability and control book written by Prabha Kuntal. Next, we are going to this IBR age. Now, what do? We have equipment or OEM models. OEM stands for original equipment manufacturers, and those are basically black boxes. So we want to use the measurements to come up with the input and output relationship. So one popular approach is called a frequency scan. Basically, we can inject sinusoidal current perturbations and measure voltage component at that frequency using Fourier transformation. There we got impedance in frequency domain. With that, we can conduct data fitting, and we can grab a transfer function or transfer function matrix. With that, we can also convert transfer function to state space models. It can be realized in various forms with state variables that lack physical meaning. So the disadvantage is, of course, we don't know the state variables, and plus it also require numerous experiments. So there's another way to do this gray box modeling. So first, the structures will be constructed from first principles. Therefore, structures are known. And then we needed to tune the barometer to match the field measurements. Depends on the field measurements, we have two methods. One is the frequency domain measurements, like we just showed. Second, frequency scan is the frequency domain measurement. Second is the time domain measurements, like the phase measurement data, the PMU data. So from PMU measurement to tune model, this has been adopted by grid industry. In the right side, I like to show one frequency domain measurement matching. So this is historically has been used for synchronous generated DQ frame, DQ axis reactance. And this figure is taken from Crossbook chapter 7.8. You can see this is the reactance in frequency domain. And there's a figure showing here. So we can tune the parameters and match that given what we know the meaning of these parameters. So with black box approach, I like to give first example. This is a black box or admittance measurement frequency again. So we have 2.3 MVA IBR. It's an inverter and this inverter is a real world inverter. How do we grab its admittance? DQ frame admittance. So this inverter will be connected to a controllable voltage source through a transformer, left side 400 volt, right side 13.2 kV. And obviously we need a very large power one. It has to be 7 megawatts. Next, this controllable voltage source will be perturbed by d-axis voltage and q-axis voltage. One by one, after perturbation, we measure the current. And the current from ABC will convert to DQ, IDIQ, and through FFT, we will grab these phasors. So make sure that we have different P and Q, and you can set up different operating conditions and grab different models because these are the linear models. It is influenced by operating conditions. One thing to mention is that the converter is really, we don't know anything except that it is grid following that you can set the PQ set point. Otherwise, anything else, we really have no idea. So this is what we got from the DQ measurement, DQ admittance measurement. For each experiment, for each case, we will measure about 40 points from 0.1 Hertz to 1000 Hertz. And you can see this is the low frequency part. It has a lot to do the PQ case operating condition. High frequency part, one condition is not too much. High frequency, it is everybody is much similar. Next, what is application for this kind of admittance? Well, we can do stability analysis. One example I'd like to give is this Wind SSO Task Force's report called the TR80 on events and modeling. One example, one particular case is called SSR, subsynchronous resonance, because of the series compensation. And how the utility people or grid industry can conduct screening is to looking at the wind farm as a source and looking at the grid as a load. So we will come up with two impedances or two admittances. With that, we will check their frequency domain stability just to use one admittance, one impedance. This is, in fact, open loop again. You convert a circuit problem to a control problem, and we can looking at its Nyquist plot or Bode plot in frequency domain. Second, we can also make sure that we can do this eigenvalue check just by looking at the roots of the determinant of the total admittance. And to do this eigenvalue check, we have to use data fitting to come up with the S-domain model, not just use these measurements. The first step, you can just use the measurements frequency domain. So that prove a lot of give a lot of advantage that can greatly save our time to do screening. The second example I like to give is the gray box modeling approach. From generic model, then we do parameter tuning. So the left is this generic type 4 wind model that people have developed. This coming from a 2010 IEEE TPW power system paper. And you can see the generic model includes the grid side converter only, and the reactive power, active power, those are included. And inner control is not included, so it's treated as a current source. The machine, the DC side and the machine side obviously not included. So with this model, we are going to match with the OEM model. Basically, the OEM should include everything to do a fault analysis. And you can see the oscillations due to wind turbine cannot be replicated, due to wind turbine rotor dynamic cannot be replicated, because the generic model ignores a lot of details from the other side. But at least we can see this is how we can do a lot of matching. So the current practices and the challenges or in IBR modeling, we'll do it one by one, looking at both approaches. For the black box approach, you can see that this admittance characterization has been used and being adopted by industry. Frequency scan is very popular for all these EMG tools. The challenge is that if you conduct everything in ABC frame, you may see this frequency coupling event phenomenon. For example, you inject 50 Hertz voltage perturbation in a 60 Hertz system, you may see both 50 Hertz and 70 hertz, right? Component in current. So this is too difficult when you do frequency, when you do FFT analysis. So therefore, we just want to have a little bit simpler way. We were going to use DQ frame. In DQ frame, you have the steady state is 0 hertz, so you don't have this frequency coupling phenomena. And another challenge is that frequency is really time consuming. A second approach is the gray box approach that the industry still use widely to do the planning study right now. Basically, for example, you have generic model. The generic model is take the example is this WAC IMS models phasor based, and we can do parameter tuning while field measurements. So the challenge is that those IMS model may not be suitable for weak grid operation, unbalanced operation, and the fast dynamic analysis that IBRs now face a lot. So before we can use any tools for this tuning, SID optimization, or those, we need to come up with adequate model structure. So therefore, many efforts have been devoted to develop generic EMT models to capture fast dynamics to make models, first principle models, more accurately aligned to the IBRs. So now, how to prepare our students for these new challenges? Not only we will now want to understand physics and simulation tools, and these EMT simulations are quite different from the previous phasor-based simulation. We also want students to be able to extract model information, then be able to use those tools called system identification, and be able to tune models using optimization and advanced computing tools like optimization. So on top of power electronics, wind, solar, grid integration, classic control, power system modeling, students are suggested to have the following course topics to be taught. For example, SID, system identification. And it is very, very useful for students to understand this and use those advanced computing tools. So in summary, we can design dynamic models from measurement data. And this approach is feasible, and it will have very good immediate importance to the grid industry. And we can use two types of approach side by side, the black box and the gray box approaches. The black box defines the input-output relationship. The gray box, it's basically you have to build a model based on first principle and then tune data using all these SID tools, like predictive model error. All these optimizations will be used. The new challenges of IBR modeling basically require university educators to actively design curricula to better prepare our students for the future. Thank you.